A warm welcome to everyone joining us today for the webinar MBE Growth of Group 3 Base Solar Cells and Other Optoelectronic Devices. I would request Mr. Varun to please share the slide deck so that we can start. I'll quickly introduce myself. I am Gunyal, your host for today's session, and I'm from the marketing team here at Skyline. So before we begin, if you can hear me clearly, I would request everyone to drop me a quick thumbs up in the chat box. A few seconds here. Right, thank you for your responses. So before we begin, I would like to share a couple of webinar notes. First, we will keep your mics muted to avoid any disruptions. Second, I would request everyone to keep their cameras on so that we have a more engaging and connected session. And third, drop your questions anytime in the chat box and we will take them up during the Q&A round towards the end. And just in case if we missed your question, you can also drop us an email at hello@orbitskyline.com and we'll make sure that someone from our team gets back to you. All right. Um, so let's get started with today's topic and welcome our speaker. So it's my pleasure to introduce today's speaker, Dr. Varun Thakur. So Dr. Varun is an MBE process engineer at Skyline with 8 years of experience in the thin film growth of gallium nitride and gallium arsenide for advanced semiconductor devices. He holds a PhD and master's in material science from JNCSR and has carried out research from across IISc, IIT Delhi, Israel, and Italy. His work spans thin film epitaxy, semiconductor characterization, and graphene-based 2D materials, including a highly cited study on nano-textured gallium nitride biosensors. So moving on to the next slide now. Um, so before Dr. Varun starts, here is a quick introduction about Skyline for those who are hearing about us for the first time. So Skyline was established in 2009 and has over 15 years of experience in delivering comprehensive semiconductor solutions worldwide. We are a trusted partner for top-tier IC manufacturers and OEMs, delivering comprehensive support across both CMOS and compound semiconductor fabrication environments. Skyline proudly embodies Make in India, Make for the World vision in the semiconductor domain and remains committed to the long-term growth of India's semiconductor capabilities. All right, moving on to the next slide now. So this, as you can see, is our clientele map. And as you can see that we have built strong partnerships with major fabs and OEMs across the globe. This global presence is a strong reflection of the trust we have built and the expertise we bring to the semiconductor ecosystem. So let's begin the session. Over to you, Dr. Varun. Dr. Varun, you are on.
I'm sorry. I'm sorry. Thank you, Gunil, for that wonderful introduction. So I'll begin by outlining my talk. So I'm going to start by introducing what is the concept of epitaxy and what is molecular beam epitaxy. So starting with the growth of group 3 based materials, and I'll be focusing on gallium arsenide as that is the material that we are mainly growing here. And then I'll talk about what are the advantages over silicon and why we want to look at 3-5 materials in more detail. Then I will take the example of gallium arsenide solar cells. I'll just quickly introduce a few basics of solar cell, like what is a p-n junction and what are the limitations and loss mechanisms of solar cell. Then I'll move on to how do we grow actually the solar cell stack using the MBE. Then I'll explain what are the different types of solar cells that have been made in the market and where the currently technology is coming to right now. So then I'll mention some features and key elements of the solar cells from the perspective of an MBE growth. Then I'll just explain some other techniques of growth uh, at the end. So then I'll finish my talk by introducing some other optoelectronic devices that are possible to grow using MBE, just to explain something about the capability of the instrument. So moving on, what is epitaxy? So epitaxy, the word comes from the Greek word epi and taxis. So it basically means above in an ordered manner, which means that if you have a crystalline substrate, then the film which grows on top of it grows in a crystalline manner. So in more technical terms, it means that there is a geometric relationship between the film and the substrate. So why are we so interested in it? Is because it provides a much better crystal structure, as you can probably imagine. There are two basic types of epitaxy, either homo or hetero epitaxy. So homo epitaxy is when the material and the substrate are of the same, the overlayer and the substrate are of the same material. For example, gallium arsenide or gallium arsenide. Or heterotaxy, epitaxy, it is when the overgrown material is different. For example, gallium nitride on sapphire. So in the figure I have shown, if the lattice is completely matched, then it is homoepitaxy. And in heteroepitaxy, the lattice may not be completely matched. And so we get a little bit of stain, which we use different methods to come into a relaxed layer. As you can see here at the bottom, maybe I'll use a laser pointer, that some of the atoms, they adjust to make a relaxed layer, right? So going ahead, now coming on to what is a molecular beam epitaxy method. So here we have an impinging flux of material which is called molecular beam. So basically what we do here is that we use material in its physical form. No chemical compound is used. The physical material is evaporated using temperature. So we use the wires to pass current, which increases the temperature, and it evaporates the material onto a substrate which is typically kept at a higher temperature. So a substrate at high temperature, it helps in movement of atoms on the substrate and to get a flatter film. So as you can see here, I have written the pressure is very low. So this is an ultra high vacuum system. So vacuum systems are classified into like low, high, or ultra high vacuum. So this is an ultra high vacuum system. The pressure is typically carried out at a pressure of 10 to the power minus 8 torr. So this is a schematic of the tool itself. Here, maybe you cannot see it as too small, but I've just given a classification of what are the vacuum levels and as I was just mentioning, low, ultra low, high, ultra high vacuum. And these are the typical features of a molecular beam epitaxy system. So it is one of the best techniques to grow crystalline wafers. So as you can see in the schematic, this is a rotating substrate. So this rotation helps in uniformity of the film. These are the effusion cells which keep the material, and we pass current. The wires are of course not shown here. This is a schematic. So this increases the temperature of the cells, and so it increases the temperature of the material inside, and it evaporates to deposit the film on the substrate. So what are the materials that we are depositing? They are controlled by these shutters. So whichever shutter is open and the temperature is high, that material will deposit. Apart from that, we have different ways to see what is going on in the chamber. For example, there are several gauges which measure the pressure as well as growth is measured using reed. Reed is a very typical instrument that is used. So the full form is reflection high energy electron diffraction. So basically, electron beam strikes the substrate and falls onto the screen, and in it creates a diffraction pattern. So based on this, we can understand what is the crystal structure of the overgrown film, right? The heart of the MBE is its pumps, which give it the vacuum. Now, one of the most important things to understand is what is this ultra high vacuum useful for? So, ultra high vacuum helps in reducing the contamination of the chamber, and so the material will not, hit against any air molecule or any other moiety before falling onto the substrate. So, this gives us an ultra pure crystalline film, which eventually, when we make a device on top of it, will be of higher quality. So the devices will have better performance. So we usually get atomically flat and abrupt heterostructure. There is no intermixing at the interface. So eventually, it all helps us in giving a better quality device. So it operates in ultra high vacuum, as I said. Liquid nitrogen flows through cryo panels. So liquid nitrogen helps in reducing the pressure. So this is basically very useful to get ultra high vacuum quality. Once we are at ultra high vacuum, then the growth takes place, and we get highly pure systems. This operation basically happens is that we start with this liquid nitrogen flow. Once the pressure falls to required levels like 10 to power minus 10, then we start to heat the K cells. The effusion cells are also called Knudsen cells, named after the inventor. And when the temperatures are at the evaporation point, then we heat the substrate to the growth temperature, and then we monitor read. So when the substrate shows features which show atomic cleanliness, then we open the shutter. Once the shutter opens, the material reaches the substrate, and we keep rotating the substrate to get a uniform coating. And then we close the reed once we don't want to see the growth anymore. And we use a recipe. So the process we can automate. So we can feed the recipe in a computer, and that will give us the film as we desire. So this is the MB system at our facility here. So as you can see,
Yes. So there is a quick poll on your screen, and I would request everyone to quickly participate in this poll. It will be on your screens or in the chat box. Please have a look. Guys, please participate in the poll. It's either in your chat box or it will come on your screen. And I'll wait for a couple of seconds. All right. So the question of the poll is MBE is what type of film growth process? Physical vapor deposition, chemical vapor deposition, sputtering, or none of the above? So we have 75% of the votes for physical vapor deposition. That is absolutely correct. Yes. So Varun, please we can get back to the slide.
yes. So here I have shown an image of the MD system that we have here. I'll just quickly explain the different parts of the system. So this here is the main chamber where we grow the film, and this is the connection to the ion pump. Behind where you cannot see is the cryo pump, and these are different other chambers. This is the load lock from where we introduce and take out the wafer, and this is the cluster tool. This basically acts as a way to transfer the wafer between different chambers. So behind we can see the preparation module. So the wafer basically after introduction into the MBE, it goes to multiple annealing processes to clean it very systematically. So at different temperatures, different cleaning processes take place before it is introduced into the main chamber. These here below you can see are the sources. These are the K cells, and these wires basically are connected to these PID controllers. So from the computer, we can give the command what is the temperature that we want, and the PID controllers control the rate at which the current flows and increase the temperature at the desired rate. Here above, you can see this is the manipulator. So this controls the rotation of the substrate. So it's a PVD system. This is correct, and this is the main functioning. So moving on. I'll just list the advantages and disadvantages. So it is a very good method for making very high quality semiconductor crystal from compounds or from several different elements. So you have the ability to mix and match different uh, materials like you can make gallium arsenide, you can make indium gallium arsenide, you can make gallium antimonide, indium gallium aluminum antimonide. So you can mix and match and make any kind of material that you want. You can make a heterostructure. So you make one layer, then you can make another layer. You can make as many layers as you want. You have precise control of the thickness of the layers. You can increase or decrease the mole fraction. So you can change the band gap. So for band gap engineering, it is very important. So it's a very versatile tool, and you have a lot of flexibility when you are making your film. So you can make them in a very precise, controlled manner, as much thickness as you want. The interface, because the shutter speed is very sharp, so very fast, you can make very precise interfaces. There will be no intermixing, and you can check that in TEM images where you can see atomically sharp interfaces. So the UHV conditions help in very high purity and very clean surfaces. So it will not have a lot of contamination like you see from different other methods like carbon and oxygen are common impurities. So these are a lot of advantages. Disadvantages, it is a very slow and laborious process. So because we are trying to make atomically sharp interfaces and single layer by layer growth, so of course it is very slow to grow. So it's basically 1 micron an hour is the kind of standard growth rate. It is lower or higher based on your specific conditions. That is why recipes are very important here. Like if you want to grow for 5 micron or 10 micron thick layer, so you need you need to let it go for a few hours. So that is why recipes are important here. The equipment involved is complex and very expensive, so it is very important to take care of many things. And a small mistake can cost a lot of money and lot of time. So in research, it is people make jokes that the full form of MBE is not molecular beam epitaxy, but it is mostly broken equipment or many boring evenings or mega bug evaporation. So these are the kind of R&D jokes that have prevented this from being adopted full scale in the industry. So even though now there is a lot of industrial use also, but we'll see that later. So I'll just explain. There are some applications. What kind of applications we have using this MBE system? So basic transistors that are the most common devices that are made in today's world, we can easily make. So transistors are one of the easiest things to make using MBE. So they just require a couple of layers, and you can make fabricate devices using a fabrication facility. Then we can also make more complicated devices like optoelectronics, like lasers, VCSELs, solar cells, LEDs. So they require multiple layers and multiple precise, you know, band gaps. So band gap engineering we need to do. Then there are other kind of devices like microwave, and then we have more fancy or sophisticated device like nanostructures or super lattices and even quantum wells. So I'll give a couple of examples, but as you can see there, it's a very versatile equipment, and we can span a whole plethora of devices using the MB system. So coming to 3,5 materials, we'll focus on gallium arsenide. Gallium arsenide is a 3,5 semiconductor which typically crystallizes in the zinc blende crystal structure.
Yes. Guys, this is another poll, another short poll that we have. So, what devices can be made using thin films according to you? Solar cells, optoelectronics, mechanical, electronic, or all of the above? So, whatever you think suits the best, please select the option. I'll wait for a couple of seconds here. This is quite an easy question, I think, and I think everyone can, correct it, select it correct in like the most correct option. We have 14 votes and we have around 48 people here. Guys, I would request everyone to please actively participate here. All right, so we have 82% votes coming in for all of the above, and 20% of you think that it's solar cells, it's just solar cells, but the correct answer is all of the above. Yes, thank you for participating. Yes, Varun, please.
Yeah, so gallium arsenide is a direct bandgap semiconductor, and for optoelectronics, a direct bandgap is much more important because it will not have any phonon losses. 1.43 EV is a very wide bandgap semiconductor. So a wide bandgap semiconductor basically it helps us in giving control to whatever devices we want to make. So in switching properties and all. So it is not always on mode. So there are a lot of advantages. I've just basically given you a hint of why gallium arsenide is useful. I'll in next slide I will introduce. I will tell you more about it. Also, there are some other factors or properties of gallium arsenide. Like it has an intrinsically low carrier concentration. It is a semi-insulating, so you can control the electrical properties, which is what is important in transistor or optoelectronic applications. So also this 3-5 semiconductor is useful for high frequency devices. It is pretty robust and insensitive to overheating. So in harsh climates also it is very useful. So when you compare with silicon, you can see that there are importance of both the materials, and it totally depends on what kind of applications that we are looking for, and that is why we choose one over the other. Another thing is that even sometimes, even in the same application, there may be some competition. So it depends on your research or what application you're looking for. So there may be an easy choice, or you may have to choose gallium arsenide over silicon, depending on your budget as well, because it is much more expensive to fabricate 3-5 semiconductors compared to silicon. So you can see some properties here. The carrier minority carrier lifetime of silicon is very high compared to gallium arsenide. So gallium arsenide has a very low minority carrier lifetime. So that is not such a great advantage. I agree. But electron mobility, on the other hand, is much higher. But hole mobility wise, silicon is better. So as I was saying, it depends on what kind of application you're looking for. And for high-speed devices or LEDs, lasers, this is where 3-5 material like gallium arsenide shines. But a lot of PFETs or other kind of transistors, where traditionally silicon has shown its advantage, that is where you may use the silicon, right? Now, let us look at what a solar cell is, because since that is what we are going to be talking about, I'll just give a short intro into solar cells. So here, solar cells we are making using a PN junction. So a PN junction is the simplest type of a solar cell where the light, when it strikes the junction, it gives rise to charge carriers. So they are called photo-excited carriers, and these charge carriers are separated due to the electric field in the depletion region. So a depletion region is formed whenever you join a p and n-type semiconductor, right? So these electrons, they will gain energy from photons, they will go to the conduction band. So we want to collect as much charge carriers as possible, and that is the whole function of a solar cell. So eventually the electrons from the top of the solar cell, which is the n type, that is where we collect the electrons, and we complete the circuit to make a current flow, right? So repeated movement of electrons through the circuit generates electricity. This is the bandage diagram. So you can see that due to this band bending, the reverse flow of electrons is prevented. So electrons cannot go back here, right? So all the electrons will be trapped here, and then we can collect it in the circuit, right? So coming to limitations and losses, the solar spectrum actually spans a lot of energy and wavelength, but unfortunately, because of our limitations, we cannot absorb most of the spectrum. So here I've given a diagram or a graph rather, where you can see the solar spectrum has a high intensity at the lower wavelength region, and but we are not able to absorb a lot of its wavelength, right? So we can absorb in the lower wavelength, but higher wavelength is completely wasted. And even in the lower wavelength, we are only able to absorb a small fraction of it. So this is defined by the Shockley-Queisser limit, that how much a solar cell can be efficient. So this is the baseline from which we start, that okay, we can make a solar cell based on a PN junction, but it will have a limited efficiency. And we have these different regions which tell us that okay, from where, what is the wavelength that we want to capture, right? So yellow is the maximum available theoretical energy. So this is where we mainly capture. Orange will not be that great because the losses because of material defects and technology are much higher. So we are not able to efficiently capture emission from this region. So blue are the losses that you get from the heat, and the pink are due to insufficient photon energy. So all this part of the solar spectrum is not absorbed. So these are all wasted due to different loss mechanisms. So now let us see how the MBE is useful for growing a gallium arsenide solar cell. So we start with a substrate. So in this specific example, they have taken a P-gas. This I've taken from literature. Typically, what we want is to grow on a P-type substrate because we want the N-type to be at the top. So we want to grow both P and N-type because we want to make a PN junction. And N-type should be at top because we want to collect the electrons from the top of the cell, because that is where the maximum electrons are generated, right? Top of the cell is where the sunlight is falling. So these different layers, what do they do? So this complete thing is called a stack. These are the individual layers, and I will explain about individual layers also. But you can understand that this is a PN junction eventually. But because there are different layers, we want to have a very high control over the layer thickness and sharp interface. So this is where the fast shutter speed of the MBE comes into picture. And as you can see, there are a lot of values here. So we have to control the doping levels very accurately as well as thickness. So the exact control over the shutter speed, it controls the mole fraction of the active layer. So for example, in gas, how much aluminum and how much gallium should be there, that can be precisely controlled using MBE. And for how long the shutter is kept open, that controls the thickness. So these are the advantages that an MBE growth gives when we are making the solar cell stack. The other things like this back metal contact are the fabrication parts. So that is not a part of the MBE growth. Now, what are the different kind of solar cells? So we have a single homo junction, which is a basic PN junction. Then we have heterojunction, multiple heterojunctions. Then we have these are more in research, but they are also being now adapted very frequently. Gallium arsenide on different material like silicon or germanium, and then reusable substrate, which is one of the most interesting things. I'll come to that. So a single homo junction, as I said, is a very simplistic kind of PN junction where we just start with a substrate and we grow N-type and a P-type on top of it, right? So typically the base is much more thicker than the emitter. So can somebody tell why the base is much thicker than the emitter? No? Okay. So basically we want the sunlight to pass through the emitter without losing energy, because we wanted to strike the PN junction to generate the charge carriers, right? So that is the basics of solar cell. But here the problem is that we cannot use the single homo junction because there are a lot of drawbacks. So gallium arsenide has a very high surface recombination velocity. There is no native oxide in, for example, like in silicon to passivate the surface. And we need to add passivation schemes to make this workable, which will add to the process complexity. So since we are anyway going to make it complex, we will not use a homo junction. We will go to a hetero junction. So this is the basic type of solar cell that is usually grown for any kind of basic study like efficiency or uh, yes, mainly efficiency. So here we have multiple layers. So the most important part about is that how are these multiple layers decided. So we have different kind of active regions, and these active regions are deposited based on the wavelength that they can capture. So here I've written like band gap is engineering is used to absorb different wavelengths. So we can use different band gap materials which will absorb uh, different areas of your solar spectrum so that you can efficiently capture as much of solar spectrum as you can, right? So the goal is to capture as much light as we can and as much region of the solar spectrum. So we reduce the band gap from top to the bottom of the cell because the higher energy will absorb at the top, and then as the energy keeps falling, it will keep on absorbing the from the lower layers, right? So this basically helps in absorbing the maximum amount of solar radiation. So here, one of the most important this thing, let's say, what can I say? Like a element, right? A fabrication, a deposition element is the window layer. So I'll explain more about it later. This gas-based window layer, it lets in maximum number of photons and reduces the parasitic resistance. So in this kind of solar cell, the maximum efficiency is reported more than 46%, and the target is to cross 50%. So keep in mind that this efficiency is not a single sun efficiency. So when we see the efficiency reported like 20-25%, those are all single cell efficiencies, single sun efficiencies. But in lab tests, we want to know the maximum capacity of the solar cell. So we shine light equivalent to multiple suns. So it could be two or three suns also, right? So let's look at one element which is called a quantum well. Because we are growing films which are nanometer thick, quantum mechanics takes over at those levels. So quantum well is basically just a region of the solar cell where one lower bandgap material is sandwiched between two higher bandgap material. So the idea is that we want to trap the charge carriers in this low bandgap region so that we can maximize the current efficiency. So basically increase the photocurrent, right? So when the light shines the solar cell, the photocurrent that are generated, if you have quantum wells in your structure in the active region, so they will all be trapped in this layer, and then the extra time that you get, that will increase your efficiency very proportionately, right? So this is the advantage of quantum wells. And I've just given the mechanism through which the current is generated.
All right, we have the last poll of the session for you, all of you. Which country is leading in the thin film deposition tool production? Germany, China, USA, or Taiwan? I'll wait for a couple of seconds for your votes. Guys, please take a look in the chat box. The poll is right there. So it's a close call between USA and Taiwan, as I can see, but the correct answer is just one. So I'll wait for a couple of more seconds here. All right. Yes, I can see that most of you have selected USA, and the correct answer is USA as well. Yes, Varun, back to the slide.
Yeah, so thank you, Gunyal. So current generation takes place through this mechanism. So quantum well solar cells are composed of a pi and diode structure. So in the inherent the I region, which is basically the intrinsic region, that is where the carriers are mostly trapped, and photo excitation causes the generation of charge carriers, and because we are trapping them in this quantum well region, so we increase the uh, current, photocurrent, right? So moving on, I will just now talk about this multi-junction. So this is the current technology. So mostly when we look at the current market, tandem solar cells are what are people usually producing. I have just taken this example, so you can see here they are basically multiple. It's similar to a heterojunction, but heterojunction represents only one junction, one PN junction or like two PN junctions. But a tandem solar cell can have like three or four. But here the problem is that we cannot have as many PN junctions as we want because the amount of energy which can penetrate through the cell is limited. So it will become as the energy of the sunlight pierces through the cell, it will reduce, and so that after three or four junctions, there is not enough energy left to justify the inclusion of multiple junctions. So here, let us look at this stack. So basically, they are individual solar cells and they have different band gaps. So I was explaining earlier that band gap reduces from top to bottom. So in this example, also you can see the top is a gallium indium phosphide on aluminum gallium arsenide stack PN junction. So where the band gap is 1.9 eV. So that is the highest. And at the bottom, you can see this gallium indium arsenide antimonide is the material which has a zero point 0.9 EV band gap. In between these PN junction, you can see something called a tunnel junction. I'll explain what it is, but basically they give a gap between the PN junction so that they don't short each other. Okay, so basically everything that we are doing is to prevent the carriers from getting out or losing due to recombination or heat. This is the primary task of a growth engineer, that how to model the growth stack so that you can increase the efficiency and reduce the wastage, right? So as for the mechanism, the photons are absorbed primarily with the by the material with the largest band gap from the top, and then as the energy reduces, the lower like the band gap reduces, so that those photons can be absorbed. So here, as you can see, the efficiency has been achieved more than 46% in lab, but the commercial has just crossed 30%, right? But as you increase the complexity, like you are making different kind of elements, different PN junctions, then tunnel junctions, so the manufacturing price also increases. So you can see here different features. We right now the industry is focusing on a low band gap region of a multi-junction because high band gap materials have been achieved through these wide band gap semiconductors. But how do we increase the efficiency of a low band gap material? That is where the industry is right now. So the challenge is in the realization where the absorber material is in the range of 1 EV. So, for example, like germanium or something like that, these are the materials that absorb at such low wavelength. And recently, one news has come that they have developed a low bandgap tandem cell, which where the bandgap of 0.75 and 1.15 eV has been optimized. So, indium gallium arsenide is also one of the contenders with a bandgap of 0.75, and they have used this to make this. Phosphide antimonide based junctions where they have made something called a Isaki tunnel diode junction. So you can read more about it. I'll not go into details about this specific example. But I would like to impress upon you that our main problem is that cost is our biggest barrier, and fabricating using these kind of complex tools adds to the cost, right? So now we want to understand how do we reduce the cost. So you can see in the Q&A also there is a question that has been asked, like how do we reduce the cost and of this kind of method. So one of the examples is reusing the substrate by removing the substrate after growth. How do we do that? We'll come to that. So before that, I will just mention a couple of elements of the solar cell manufacturing. So anti-reflective coating is one of the most interesting and important aspects. So what they do is whenever the sunlight strikes the top of the solar cell, most of it reflects back. So if the sunlight does not penetrate through the solar cell, it will not generate the charged photo excited carriers. So the anti-reflective coating helps in mitigating that. So how do we do it? We usually use made of aluminum gallium arsenide, and we use sodium hydroxide to roughen the surface and cause like small pyramid-like structures, which reduce the reflection from the surface, right? So it increases the transmission coefficient and traps the light so that it is forced to go inside the solar cell and not get reflected back. So here also we can do a lot of engineering. Like for example, the thickness is chosen such that the only destructive interference takes place, and so we destroy any kind of reflection, and we minimize the reflectance for which at the wavelength for which photocurrent is lowest, right? So these are all things that we have to keep in mind when designing the ARC, which is anti-reflective coating, right? So that is why the current density is maximized. So the current of all cells will be matched, and current of the bottom layer is greater than top cells. Okay. So I'm not going to read through this. Now coming to the next element, tunnel junction. So tunnel junctions are what I showed earlier. They are basically the spacer layers between two different PN junctions. So what happens is that if you have a PN junction and there is a PN junction below also, if the N of the top layer touches the P of the bottom layer, then they also cause loss of charge carriers. So to prevent that, we make something called a tunnel junction, which is a low resistance and optically low loss connection. So we don't want the charge carriers to be lost due to resistance in the circuit. So the resistance is low. So how do we make that? We make that by making it a very highly doped uh, junction, right? But the band gap is higher. Okay, so the band gap is higher, so that prevents the uh, charge carriers from getting lost due to their normal motion. So we have tunneling and low resistance as their main transfer mechanism. So the charge carriers transfer through the to the next PN junction, but they do not get lost in the circuit uh, due to the high band gap, right? So now the second key element is the window layer or backscattering field. So as you saw in the slide where I showed this heterojunction solar cell, we have something called a window layer. So the purpose of the window layer is to let in maximum amount of sunlight, but prevent the carrier from going back. So the same thing happens in the backscattering field also. So at the bottom of the solar cell as well, we don't want the charge carriers to go out in any other method except for the circuit, right? So how do we do that? We again employ a highly doped heterojunction, so that prevents the charge carriers. Basically, the highly doped heterojunction repels the charge carriers into back into the cell, so that the charge current generation becomes higher, right? So these are the two main elements. So I hope you can understand that all these elements are basically used to increase the efficiency of the solar cell. So now I'll just move on to some different kind of solar cells that have been uh, grown in the recent past. So using silicon or germanium as the substrate. So gallium arsenide growth requires a good quality crystal. So usually we grow on either gallium arsenide as well as or some lattice match or cheaper substrate. So we need the overlay to be the least defective, but also to be cheap, right? So how do we match both the things? So what people have done is to reduce the cost. They have used to grow buffer layers. Okay, they have used buffer layers. These buffer layers incorporate the defect, so the film grows later defect free, right? So on silicon and germanium, the solar cell, which have been grown in 1989, have exceeded 22% efficiency. And in 2008, IMEC has reported a conversion efficiency of 24% for the single junction gallium arsenide. So keep in mind that it is much higher now compared to what was grown earlier. So research is still going on, and now they are targeting a conversion efficiency of more than 35%. So 3-5 materials are currently in focus, and continuous improvement is going on, and we are targeting to grow multi-junction solar cell with an efficiency of more than 35%. Now, this is the most interesting aspect. Like, cost of material is very prohibitive, right? So if we have a very expensive material which gives a very good solar cell, like a substrate, but you can only use it once. So then the cost becomes very prohibitive. So reusable substrates are a godsend. So basically what they are doing is that we take gallium arsenide and we separate the substrate after growth. So as you can see here, this has taken an example of germanium. So germanium has been used to grow the film and then it has been taken off. So how do we do that? We do that by using something called a sacrificial layer. So we dissolve that sacrificial layer, which prevents the substrate from sticking onto the film. So the film is then, free floating, which we can transfer onto glass or some other cheaper substrate, right? So photovoltaic cells made using this process have exhibited efficiency of more than 24%. The problems here happen that sometimes these free floating films will crack or they will, get destroyed. So this is not without its own set of issues, but they have been, proven to give an efficiency of more than 20 or 25%. So epitaxial liftoff is the process through which we can achieve this. So what I was telling, I can explain it much better here. So as you can see in this schematic, so we deposit a sacrificial layer, so thin film of a material which can be selectively etched away. So we use a solution which only etches away that specific layer, and we grow that on a gallium arsenide substrate. So usually it is a high aluminum content aluminum gallium arsenide, and then on top of this, because it is already lattice matched, so then we can grow a solar cell on top of it. It grows very nicely and it will give you a very good efficiency. And then we, just to use this substrate again, we dissolve the aluminum gallium arsenide sacrificial layer. How? By dissolving it in hydrofluoric acid. So this does not affect your overlayer, which is the solar cell, and then you get the substrate back. So you can use the substrate again. So previously, ELO had issues. We used to see these microscopic cracks in the lifted off films, and which increases with area. They used polymer support layers, but they also caused strain. Again, there were cracks. But now photoresists have, with silicon support, they have given crack-free lift-off. So this was a research problem. This has been resolved. So imagine like what all we can achieve. We can achieve growth on glass, which for any engineer is like the gold standard, because glass we cannot use to grow directly. We must grow on a silicon or gallium arsenide crystalline sample because they are epitaxially matched and they are clean room compatible materials. Clean room means MBE compatible, but glass is cheap. So if we can grow on these crystalline films and then transfer them onto glass, then we can make cheap solar cells. So this has been achieved now. This I have taken from a very highly cited paper. So this has been achieved already. So this concludes the part of my talk where I talk about solar cells. I hope you have understood a lot and you have understood how we have made the process cheaper through different engineering, methods. So now I will just tell you about a couple of other kind of devices that are possible to grow using MBE. So laser diodes are one of the most interesting semiconductor devices. They are basically same as LEDs, but it is just that we can get lasing out of this active region. So same thing, like because we can make quantum wells with nanometer level thickness, which can give quantum confinement and then we can get lasing using this active region. So we can fabricate laser diodes. They are basically PIN diodes, and the gain is the intrinsic region only. So it acts like a Fabry-Perot laser. You can see the shining part is there, top and bottom region. So the light is trapped between the two reflective regions, and the lasing happens through the side. Okay, so this is a very standard device. The working principle is given here. Voltage is applied across the laser diode, and once the current is injected, and the reflection between the two reflecting surfaces, uh, that increases the current uh, in the device, and the photons are emitted in the from the side, right? So stimulated emission, when it is achieved, then we can get coherent laser output. So the advantage is that we can get only certain wavelengths. So you can design it in such a way that only specific wavelengths are emitted, right? Then now the second device I would like to talk about is this quantum well infrared photo detectors, or QIPs. So they take advantage of this inter-subband transmissions or transitions. So here we take advantage of these band states within the conduction band. So an electron, when it goes from uh, one inter-subband to another one, it absorbs in the infrared region. So this is not possible in bulk. So through MBE, you can grow like these thin films, which are in nanometer region, and which will give you these band states. So you can use this like you can make this infrared photo detectors. So the advantage is that infrared detection is a very challenging aspect of device physics. So using this ME, we can grow such kind of films which take advantage of this quantum well technology to get this infrared photo detection, right? So quantum well, as I already explained, they collect photo-excited carriers trapped in the wells, and so the photocurrent increases. And in 3.5 material, uh, these materials do not absorb in infrared, so we use these quantum wells to make them absorb in the quantum well region. So here you can see a schematic where you can see, because of these low thickness, the inter-subband transitions dominate, and so when they are trapped in these quantum wells, we can take them out and we can get IR absorption. So, in conclusion, MB is a versatile tool which gives you a very high control and gives very clean and pure films. It is a very expensive and complex instrument, and requires a lot of money to operate, and a lot of care to keep it running. It provides in situ monitoring and atomic control over the thickness of the layers. We have the latest technologies that we can grow using this tool. So we have both 3.5 as well as 2.6 transistors, optoelectronics, or MEMS, or different kind of devices. We just grow the stack and then we fabricate. So it's a very versatile and flexible tool. You can use it to span the entire semiconductor ecosystem, I would say. Even though the main disadvantage is that it is a very slow and very long process times. So take home message is that it is very complex and expensive instrument, but it has some specialized uses. It's primarily used in R&D, but it is now beginning to find use in industry device fabrication as well.
All right. Thank you so much, Varun, for such an insightful session. And today's session offered a remarkable technical perspective on how MBE enables next generation 3.5 solar and optoelectronic devices. Now, I would like to open the floor for your questions, and we'll take up a few questions now, considering the time constraint. And in case we miss your question, you can anyways drop us an email at hello@orbitskyline.com. And I'll also add this email ID here in the chat box for all of you, and we'll promptly get back to you. Okay, so Varun, the first question we have is what It's by Ramesh, and he's asking what are the main limitations of MBE that a new researcher should be aware of apart from the cost.
Yeah, cost for a researcher is not the thing that they should be worried about, right? Because the cost is for the industry to take care of. So main limitation is that you have to be very. I mean, there are too many parts here. So you have to be very careful that you have checked all the boxes. So it's not a very simple method. So you have to be first of all sure that your wafer is clean enough. So it starts from cleanliness and the recipe is correct or not. So because it takes a lot of time and effort to grow a film, so any of these smaller mistakes that the wafer is not clean enough or you don't have liquid nitrogen, so these are all the main limitations. So because it is very complex, you have too many things to take care of while you're doing the process. So it's not like a single button we press and it is done, right? So the complexity is the main limitation, I would say.
All right, thank you, Varun. The next question is I have one doubt. Can you explain the main loss mechanisms in solar cells? Is it optical recombination or resistive losses? And the question is by Shagun.
Yeah, Anzad has already replied. I think he is much better in solar cell technology. He's right that all the loss mechanisms are there. So when we are growing the films, so I'll speak from an MBE perspective. So there are different things here. So when you're talking about solar cell, one thing is your growth of thin films, which is what we are talking about here. In the thin film technology, the MV growth is what we are targeting. So the recombination losses are what will dominate. The optical or resistive losses, they will come in the device, space. So one thing is to get the stack, and another thing is to fabricate the device itself. So we can take care of one loss mechanism in the film, but we have no control over the other loss mechanisms, right? So recombination is what I will say from the MBE perspective.
All right. Thank you. I hope your query is resolved now. And the next question is by Jayanta. And the question is, as you mentioned, carrier are trapped in the quantum well. What kind of engineering you do to extract carriers to the external circuit?
No, we don't do any engineering. This is basically how the circuit is designed. So if you see here, so this is the circuit, right? So what we do by trapping the carriers in quantum wells is by increasing the time that the carrier has before it recombines. So once the time is increased, anyway the carriers are flowing through the circuit. So instead of recombination, they just get collected through the normal circuit. So we don't do. I mean that quantum well design or its presence itself is the engineering.
All right, we have a recent question by Suresh. I understand that the MBE usually are lab scaled, but are there any companies making MBE for high volume fabrication? If so, what are they and who are using?
Okay, who is using? I don't know. I know that Rebel is making. What is happening is that there are MBE systems where you can grow multiple wafers at a time. So right now here what we have is we can grow only one wafer at a time. But we have holders where we can grow three different small pieces at a time. But this is lab based. So in industry standards, we need more volume. So I think Ribbon has recently launched a dual chamber MB where they can grow, I think, eight eight wafers at a time. But I don't know who are their customers, so that I am not aware of.
All right. So the next question is directed to our HR. She is present here. She is Manya from the HR team here at Orbit and Skyline. And the question is by Pankaj. And the question is, how can a mechanical engineer join Orbit and Skyline, and what skills are required? So I would request the organizer to unmute Manya's mic and let her speak.
Hi everyone. Am I audible?
Yes, Manya, you're audible.
Okay. So thank you so much, Varun, for the wonderful session. It was really informative. So I'll start with Pankaj now. Hi, Pankaj. Thank you for your question. Yes, the candidates with a mechanical engineer background are absolutely eligible to apply. We have multiple positions where mechanical engineers they fit very well, but it purely depends on your skills, experience, and interest. I would encourage you to kindly explore the opportunities we currently have open. All our active job postings are regularly updated on our career website, and we also share them on our LinkedIn pages on like for early access. So you can go through the role descriptions and check the eligibility criteria, and please feel free to refer to those platforms and apply to the roles that match best your profile. Like, thank you.
Thank you, Manya, for answering the question. And we'll be taking up the last question. And the question is by Mayur, and he's asking in photonics now in industry, they are using gallium arsenide lasers for transistors. So this is the question for you, Varun.
I'm sorry, I was photonics, right?
Yeah, in photonics now, are they using gallium arsenide lasers for transistors?
Uh, I don't understand the question. I mean, it's a statement or a question? They are using, yes.
Okay, I think that's a question he is asking. So it's okay. All right.
Yeah.
So guys, okay. So wrapping up the session, if any of your questions are left unanswered, don't worry, you can drop us an email, and I have pinned the email ID here in the chat box, and we'll get back to you. And thank you, Dr. Varun, again for the detailed explanations and for answering the audience's questions so clearly. And lastly, we'll be sending out a follow-up email shortly with the webinar recap video link and the slide deck as well. So you can catch up on anything you missed or want to revisit. And thanks again, Dr. Varun, for the enlightening session. And thank you to all our attendees for joining us today. And we hope that you found it valuable, and we look forward to connecting with you again soon. Thank you, everyone, for your time.
Thank you, Gunial, for hosting this webinar. Thank you, everybody, for joining.